who will introduce Dave? Are you going to introduce the speaker, or Jimbo will introduce the speaker?
Yeah, Jimbo, do you want to, as chair, would you like to unmute yourself and then do it?
Yeah, sure, I can do that. Since Shulei, Wang, and I are supposed to take care of this semester. So I think we will just start. Hello, everyone. Welcome to the statistics seminar. It is a great pleasure to have Professor Jingyi Jessica Li to speak today. Professor Li is an associate professor in the Department of Statistics at UCLA. Her research is at the interface between statistics and biology about developing new statistical methods for understanding biological questions. Today, she will be talking about the Neyman-Pearson paradigm for asymmetric binary classification. So without further ado, let's welcome Professor Li.
Thank you very much for the introduction, Professor Liu, and thanks Dave and Tandy for the invitation to give this special seminar. So today I'm going to talk about my collaborative work with a few statisticians about this Neyman-Pearson paradigm for asymmetric binary classification. So I joined the efforts with Professor Xin Tong at University of Southern California, who started working on this since his PhD, and also Professor Yang Feng at NYU, and also my former student Vivian, who is currently at Rutgers, and my current student Eileen, still at UCLA. So thanks to their joint efforts, we have been working on this topic for quite a lot. So as an introduction, I'll first talk about a few notations and concepts in binary classification. In binary classification, we have features as p-dimensional random vectors, and we have binary class labels. And this is a prediction problem. Our goal is to find a function, which we call a classifier, that maps from this p-dimensional feature space to the binary space. So the goal is that given a set of input features, say clinical characteristics of a person, we want to predict that person's disease status. This is especially relevant in this current time. And to code the status as a binary indicator, here by our notation, we refer to 0 as the disease class, 1 as the undiseased or healthy class. And this is particularly important because we will make use of this 0-1 notation throughout this talk. Okay, a classifier is a binary function, but how do we construct it? We rely on training data. So here is a standard notation for training data set. So we have m observations in this data set, and each observation is a pair of features and class label. So in this talk, we refer to an algorithm for constructing a classifier from training data as a classification method. For example, we have logistic regression, support vector machines, and random forest as three methods. A classification method is a way to construct a classifier from training data. So here, our classifier, we added this hat notation because we want to emphasize that this classifier is a function based on the training data, and as a result, it is random because we consider our training data as random. And we have 3 evaluation criteria for a classifier. So here we denote xy as a general notation for a random variables following the same joint distribution as each observation in our training data. So based on this notation, we can define the classification error, or we call the risk, as this probability. Sorry, there's a typo. So this should be phi hat x doesn't equal to y. So what this means is that we made a mistake in our classification, and what is the probability? And by the probability law, we can decompose this as a sum, as the conditional probability here that the true label is 0, but we predict it as 1. We call this as the type 1 error, and the type 2 error here R1. So please note that type 1 error corresponds to R0, type 2 error corresponds to R1. And this risk can be written as a weighted sum of those 2 types of errors. And the weights are the probabilities of the class label being 0 and being 1. So here we use different colors for different probability distributions. So here the pink one is regarding the joint distribution of X and Y. And the blue one is regarding the distribution of Y. And this orange and this red notations are referring to the conditional distribution of X given Y equals 0 and given Y equals 1. And sorry, there's another typo because I made the notation change last minute. So all these probabilities are conditional on the classifier phi hat. So as a result, because of these are functions of phi hat, and if phi hat is a random whose randomness comes from training data, then we can say all the three criteria are random when the classifier itself is random. Okay, so that's the notation. And in my talk, I will focus on the Neyman-Pearson paradigm. What does it refer to? So to define it, I mean, to contrast it against what we're familiar with, we have the classical paradigm and the NP paradigm for contrast. So here, to compare them, I talk about them in the ideal case. I look at their oracle classifiers, which means that we can find the best binary function as the classifier, and this oracle classifier is not data dependent, it's not method specific, and therefore it's not random. But in practice, we cannot find it. So this is only in theory. And in the classical paradigm, the oracle classifier I call phi star is the minimizer of the risk. In contrast, in the NP paradigm, the oracle classifier is a constraint minimizer of the type 2 error with the type 1 error controlled under alpha. So actually, I can change this inequality to equal because I know that as my type 1 error becomes smaller, the type 2 error will become bigger. So therefore, this minimization will be taken when R0 phi equals alpha. And under this constraint, I want to find the corresponding minimizer for the type 2 error, and I call that phi alpha star. So I'll give a review about the history later. But this picture is showing a direct contrast. Okay, in the classical paradigm, if we think about the simplest case where our feature is one-dimensional and follows two Gaussian distributions under the two classes, then what we'll find is that the classifier will be a cutoff or a threshold on this one-dimensional X. Where should we set the threshold is how we construct the classifier. So in the classical paradigm, we vary the threshold until we minimize the risk, which is the area, overlapping area here. And in the NP paradigm, we have a pre-specified alpha as the upper bound we want to place on the type 1 error. And then we find a threshold that satisfies this criteria, and we end up here. So you see, under the NP paradigm, because we prioritize the type 1 error, of course, our type 2 error will be bigger than what we achieve under the classical paradigm. But what we achieve is that we can control the type 1 error, while under the classical paradigm, we treat the two errors in a symmetric way, and their weights will be determined by the marginal distribution of y. What is the probability of y equals 0 and y equals 1? Okay, that's the oracle sense. And where did the name Neyman-Pearson come from? So we are familiar with this Neyman-Pearson lemma in hypothesis testing. And this is where we borrowed the name from. So in the hypothesis testing, we care about the power given a significance level. And the Neyman-Pearson lemma gave us a very important result about the most powerful test of level alpha. So this is aligned with our goal under classification as well, because when we have the largest power in test, it is equivalent to having the smallest type 2 error. And that's what we want to achieve in Neyman-Pearson classification. Okay, so then the question is, why do we need this NP paradigm for classification? So there are several scenarios where this is desired. The first scenario is that when the two classes have asymmetric importance. For example, in cancer diagnosis. So if we call class 0 as cancer, class 1 as normal, then when we mispredict a normal sample as malignant, then the cost will be patient anxiety, additional medical cost, that's associated with the type 2 error. However, if we make the other type of error, that is we mispredict the tumor sample as normal, this could be life loss. So it is clear that in this scenario, the two types of errors have very different importance. So we want to control the type 1 error to be very small. And often, for talking to doctors, we realize that they often have a pre-specified threshold on the type 1 error. The reason is that this is very human interpretable, right? We are very sensitive to small probabilities. When we ask a doctor, he or she may say, okay, 1% is small or 0.1% is small. And these can be reflected on this alpha.
You want to walk down to that other guard?
Okay, and sorry, wait. Okay, the other scenario is that when the two classes have imbalanced sizes. So let's revisit this notation. So we see that the weights in the risk are the probabilities of y equals 0 or y equals 1.
You need to get back to.
Sorry, can I interrupt for a second?
Yeah,
Is that someone's mic?
Probably.
Okay, whoever is walking the dog, I think.
So one of the hosts could actually mute the person who's not muted. There's only one person who's not muted.
Let me see.
He's muted now.
Okay, great. Sorry about that.
No problem. Okay, so when the two classes are severely imbalanced, for example, if this class 0 has much smaller probability than the class 1, right? So in this case, then what we will do is that when we do the minimization, we will tend to shrink the type 2 error as opposed to type 1 error. And then the classical oracle classifier may end up having an excessively large type 1 error. So that's not good. And when that happens, we may want to put a threshold upper bound on the type 1 error. And that will fall under the NP paradigm. And moreover, there are scenarios where data may have distortion. So for example, this is an application work of my collaborators who recently published this in JASA Cases and Applications. So here they investigate a very interesting question about censorship in the Chinese version of Twitter. So they've analyzed the Twitter post and found that because of censorship, so the proportion of tweets that talks about some social issues are not reflecting the real proportion in the population. So therefore, there is some data distortion that changes the probability of y equals 0 and 1 in the data as compared with the population. So in that case, if we talk about the risk, then the empirical risk on the data can be totally off compared to the population risk. But if we look at the type 1 error and type 2 error, because they are conditional probabilities conditioned on y, so therefore they will not be affected by that censorship distortion. So that's also a case where we should use the NP paradigm. Okay, then formally, this is the definition of the NP paradigm. It seeks a classifier that satisfies this constraint objective function, and alpha is a user-specified level, often small. So the earlier work in this topic stemmed from the engineering community more than a decade ago. And then my collaborator, Dr. Xin Tong, and his PhD advisor, Dr. Philip Rigoulet, started their endeavor in the theoretical work of the NP paradigm since 2011. And I joined his efforts when we try to really make this paradigm practically work. And that will be our focus today, the NP umbrella algorithm. So previously, these discussions were about the theoretical properties of the NP paradigm. And in this 2018 paper, we proposed an umbrella algorithm that can adapt those popular classification methods, such as logistic regression and random forest and support vector machine, and even neural networks to this NP paradigm. And that will be the focus of my talk today. And these are more recent works. I'll just briefly mention them. For example, this parametric work is trying to reduce a sample splitting we require in the umbrella algorithm, which you will see later. But the price we pay is that we need to add some parametric model assumptions. And this is the paper I just mentioned about that censorship application. So I'll focus on the umbrella algorithm. So
Sorry,
here,
can I ask a quick question? Can you go back 2 slides?
here.
Yeah, can you repeat the point you made here about how something doesn't depend on unknown?
The wise distribution. So in this, it's about the third case, which I will not talk in detail today because I'm not involved in this work. But I can say that the idea here is that we focus on looking at R0 and R1 instead of R, because in the data, the proportion of Y being 0 or being Y is distorted. So that's why if we look at the risk, the empirical risk R hat is a biased thing for the population risk R. But if we only look at R0 and R1, then the empirical R0 hat and R1 hat, they are not biased. That is for that specific application.
Okay.
Yeah,
okay.
Yeah. Okay.
Okay, all right, thanks.
Thanks for the question. All right, so here is about implementation, right? We talk about Oracle, but we need practical classifiers which should be constructed from data, and they depend on the classification method, and they're random. So we know that under the classical paradigm, a popular way is to do the empirical risk minimization. You can consider this empirical risk as your loss function, and you minimize it to find the practical classifier. But under the Neyman-Pearson paradigm, how should we do it? A very natural thought would be, how about we also do this plug-in? We replace R0 by R0 hat. That's the empirical type 1 error on training data. And we minimize this R1 hat, the empirical type 2 error on training data. Would this be a good solution? Right, this is an analog to the classical practical classifier. Unfortunately, this is not a desirable classifier under the Neyman-Pearson paradigm. The argument or the reason is that although this classifier would have its empirical type 1 error controlled on training data, however, its population type 1 error, this thing, is not guaranteed to be under alpha with high probability. And so then our question is, why would we care about the population type 1 error instead of the empirical type 1 error on training data? So here is a cartoon I made and posted on YouTube. If you're interested, you can check it out later. So this is a toy example about why is this population type 1 error important in medical diagnosis. In this toy example, we have a one-dimensional feature. And this feature would indicate how likely this person may have a disease. So the reddish color means this person is more likely disease, and the bluish color means this person is less likely disease. And the binary label here is marked as plus and minuses. Plus means having the disease in reality, minus means not having the disease. And in this case, a classifier would be a cutoff on this one-dimensional measurement. How should we call a person, that diagnose a person as disease or not? So if the question is that if we want a doctor would like to control the false negative rate under 1% while minimizing the false positive rate, where should be the diagnosis threshold? So here we listed 5 candidate thresholds, and we see that as we go down, we will diagnose more people as diseased. So we want to choose among them to see which one is the best, satisfying this false negative rate desire. If we can observe the whole human population, then that's not difficult. We can just do counting. And we know it ended up being threshold 4. That's the oracle. However, in reality, we don't know the whole population. As a doctor, we can only observe a random sample from the population. If that's the case, then where should we set a threshold? If we still do counting, then we would actually select threshold 2 based on the sample. However, when we know the truth, we would calculate the population level false negative rate, and that will become 7%, higher than 1%. If we have another random sample, we will pick another threshold, and we can repeat and repeat and again. Then we will get a distribution on the thresholds selected on random samples. And then we can see that for about half of the chances, we will end up selecting thresholds not desirable. So this is a very simple illustration to see that if we simply set the empirical type 1 error to that 1%, we may end up with thresholds whose population type 1 errors or false negative rate here are greater than 1%. This is the motivation of controlling the population type 1 error. So a related paradigm, which I'll talk briefly in the end, is called the cost-sensitive learning. So this one is very popular in practice. What it basically does is that they change the weights of the type 1 and type 2 errors in the objective function from the probabilities of y equals 0 and y equals 1 to some arbitrary weights. So if they put a weight on type 1 error to be large, then naturally you will get a classifier with a small type 1 error. However, for medical diagnosis, the difficulty of using cost-sensitive learning is that we do not have consensus to assign costs. Because compared with the type 1 error probability upper bound alpha, the costs do not convey very easy interpretation. Especially when we talk about medical diagnosis, we may face ethical issue to talk about the cost. Okay, so for example, if this is our target, right? For a random classifier, if we want to control its population type 1 error under alpha with high probability, why do we talk about probability here? The reason is that, as I said in the beginning, this phi hat is random. So it's R0 is still random. So therefore, as a random variable, we talk about its probability. We want to make sure that it falls under alpha with very high probability. And this probability is indicated by 1 minus delta. So delta is said to be very small. However, in the cost-sensitive learning framework, it's not easy to see, okay, given this alpha and delta, how do we design the cost? So this is actually related to our ongoing research. I'll talk in the end, but let's leave this question here for now. So another thought is that how about the ROC, receiver operating characteristics, something people use a lot to evaluate classification methods. So in this illustration diagram from Wikipedia, so we can see that this is the ROC space. And so in our language, the x-axis is type 1 error. The y-axis is 1 minus type 2 error. And the good method should have a curve very sharply arising and be flat like this. That will be a perfect classification method. Okay. However, we know that in practice, to be able to plot the ROC curve, we can only use empirical type 1 and type 2 errors. So even though we may use some test data or use cross-validation to calculate the empirical type 1 and type 2 errors, but our argument is that even if we do that, we still cannot really control the population type 1 error. So here's another toy example. So in this toy example, again, we used a very simple case, one-dimensional feature following two normal distributions with different means and two classes with equal probabilities. And then a classifier would be an indicator function by setting a threshold on this one-dimensional feature. So the nice thing about this toy example is that we will have a closed form formula for the population type 1 error and one for the population type 2 error. To illustrate our point, we simulate training data with sample size 1,000. So based on a training sample like this, right, each of the data points can serve as a candidate threshold. So we can naturally have 1,000 possible classifiers for each threshold. And then we independently simulate a test sample with size 1,000, and we repeat this whole simulation for 1,000 times. So let's see what we do. This is actually the ROC based on that 1,000 classifiers. So these 1,000 classifiers in one simulation. And for each of these classifiers, we evaluate their empirical type 1, type 2 errors on the test data. So that's what we get. So if we want to control the type 1 error at 5%, the natural thing to do is to draw this vertical line and pick this threshold to the left or on this vertical line. So we pick this yellow one. That gave us one selected classifier from the first simulation. From the second simulation, we do the same thing. We select another classifier. From the last 1,000th simulation, we do the same thing and we get a classifier. So we end up picking 1,000 classifiers, one per simulation. And we evaluate their empirical type of error on the corresponding test data. Of course, they are all controlled because that's how we selected them. But if we evaluate their population type of error using that closed form formula, unfortunately, they are not satisfying that high probability control because you see a large proportion of them have population type of errors greater than 5%. So clearly, this ROC approach based on empirical type of errors will not satisfy our purpose. So furthermore, I want to make the point that because the ROC is comparing classification methods based on empirical type of error, so we cannot really say which method does better if we have a population type of error target. For example, if we want to compare two methods when we want to control the population type of error under 10%, then it's right here, but we don't know what's happening here because the x-axis is not about population type of error. So we see the implementation difficulty. And now I'm going to introduce our major result about the NP umbrella algorithm. So this is our formulation. Suppose that we have an alpha defined by the user, and we want to control the classifier's type 1 error, population type 1 error under alpha with probability at least 1 minus delta. So this high probability setup. So our goal, the practical classifier should be the solution of this. So we minimize the the empirical type 2 error subject to this high probability constraint on the population type of error. So you see, it's not like that plug-in constraint formula I showed before, because we're not just constraining on the empirical type of error. Instead, we're talking about this in the population type of errors, high probability control. That's the goal to be satisfied by our NP umbrella algorithm. But how to achieve it? So I will talk about this algorithm by its high-level insight. So we want to make this algorithm work for all the scoring type classifiers, such as logistic regression. And here, a classifier is constructed from a scoring function and a threshold. So the scoring function is often we obtain from training. So for example, this is the scoring function we have from logistic regression. So it will be our estimated probability of y equals 1, given x takes this observed lowercase x. And we need a threshold to set on the scoring function to make binary decisions. So we can write this classifier as an indicator function that the scoring function applying to a data point feature is greater or equal than the threshold. Okay, so under the classical paradigm, only this S hat needs to be constructed from training data. Because, for example, in logistic regression, this t will be set to 1/2. But under the NP paradigm, this t is unknown. We need both this S hat and the t constructed from the training data. And what we input is the alpha, the type of error upper bound, and the delta, which will be that high probability thing. So 1 minus delta is called a high probability, and we call delta the violation rate. So actually, I saw there are some questions in the chat box, Dave. So should I go ahead and answer them now?
You know, I was just typing about this, and I was thinking that if people wanted to ask them right now, they could unmute themselves.
Oh.
But otherwise, at the end of the talk, we could look at these.
Okay.
I don't know. I mean, just looking at the chat, Feng, would you like to ask a question now? Or?
Yeah, maybe that would be good, right?
Yeah, Jessica, hi.
Hi.
I think we were having a discussion there is, when you describe that randomness of phi hat,
yes,
I think that somehow depends on how you obtain phi hat.
Exactly.
So for example, even for logistic regression, when you have different number of parameters, that randomness could be different. So, and also the loss function would be relevant. You know, you use log likelihood versus another loss function, the randomness would be different.
Exactly.
So yeah, I'm just curious whether that's something you're gonna address, but maybe I should leave you to describe the NP algorithm first.
Yeah, sounds good. Yeah, that's a very nice question.
Okay.
Yeah, we'll discuss that later. Okay, so that's the challenge here. We need to estimate both this, get this S hat and also the threshold, so we can construct a classifier from training data. All right, so this is the strategy we want to use to achieve this. So we rely on sample splitting. So the splitting will be a nice thing to give us independent things, as we will see. So we split training data into two parts. One part will be a mix of class 0 and class 1 data points. So on this mixed sample, we will train a base algorithm, such as logistic regression or random forest, to obtain a trained scoring function, S hat. And then we apply this S hat to some left out class 0 sample. Then we'll convert those left out class 0 observations into classification scores. So our goal is to find the threshold T among those classification scores. And we do threshold search. So our idea is that to search among those scores and choose the smallest threshold on the classification score, such that the violation rate, for example, this violation rate is the delta, right? So we want to control this violation rate under the predefined delta. So the violation rate would be the probability that the population type 1 error exceeds alpha. So here I want to make a point that when we talk about the scoring function, so we are assuming that a larger classification score would be more indicative of class 1. So because of that direction, we choose the smallest threshold, because we know that as we increase this threshold further, we will predict fewer class 0 as class 1. So we will further reduce the type 1 error, but the price will be inflating the type 2 error. So that's why as long as we can satisfy this violation rate control, we pick the smallest threshold as we can. And to achieve this, we actually utilize the order statistic technique to help us find the threshold. So that will be what I'm going to talk next. Okay, this is a famous lemma from textbook about the distribution of order statistic for IID random variables. So here we have n random variables IID, and their common CDF is F. So then we denote by TK the kth order statistic. So in this case, we order them and pick the kth one. So this order statistic can have the right tail probability in this number. And we know that here in this number, F is the CDF, right? And T is from here. And we have this combinatorics number. So how do we make use of this result? This is something very interesting. If we replace this T by this number, F inverse 1 minus alpha, and then we change the direction from greater than to minus, then we can actually still have this upper bound on this based on a combinatorics number, but now on the right hand side, we can remove the F because it's canceled by this F inverse, and we're just left with alpha. So here on the right hand side, we have three things: the order K, the alpha, or two things, the order K and the alpha. So if we can use this thing and try to make this under the violation rate delta, then we're done. So how do we achieve that? So based on this result, we can have this main result for the algorithm. So let me try to give the setup so we can see the connection. So let's say that we train a classification scoring function from the mixed sample in the sample splitting, and we apply it to the left out class 0 sample with size n. Then the resulting classification scores T1 to Tn would become real value random variables, classification scores. So when all the observations are independent, right? And when the class 0 samples, they follow the same distribution of x given y equals 0, and they're independent, then we can say that these classification scores, T1 to Tn, they are IID. And this IID result does not depend on which classification algorithm I use, because this is just endowed by the data independence as well as the sample splitting, random sample splitting. So with these n scores, we denote by TK the kth order statistic. Okay, and then if we choose this one as our threshold, what will be the classifier? That will be for a new observation, let's say call it X and Y. We apply this trained scoring function to it, then we get its classification score, and we denote that by big T. So our classifier would just be this indicator. When this T exceeds this candidate threshold TK, we predict class 1. Otherwise, we predict class 0. That will be the classifier. And then what would be the population type 1 error of this classifier? Then it will be the probability when this T is corresponding to an observation coming from class 0 and it exceeds this threshold. So here the randomness is twofold, right? The randomness is actually coming from the randomness into TK, because the randomness of T will be taken care of by this P. That's regarding the distribution of the class 0. So it takes care of this. But TK is a threshold picked from training data. So it stays here as a random variable. So therefore, when we write down this type 1 error, we can see that it becomes a function of this TK. So the threshold will stay here. And the randomness from the training and from the left out class 0 sample is all aggregated in here. And also, we know that because we apply the same trained scoring function to the left out class 0 and to the new observation, we can have this T and T1 to Tn follow the same distribution CDF, which we call capital F. So that's the CDF for every score from class 0. So we have this as the population type 1 error. So when we write this violation as the population type 1 error exceeds alpha, then by a simple inverse, we can get this formula. So that's why this lemma 2 will give us the upper bound on this violation. That's here. So now this formula will give us a very simple result. As long as we can control this under delta, we satisfy our purpose. So I can say that previously, when we first approached this problem, our first thought was not using this order statistic technique, but instead we used bootstrap to help us get the distribution of type 1 error on some left out data. That's what we did. But then we realized that, interestingly, no matter what classification algorithm we use, we roughly end up with having the same order in the left out scores. So that made us realize, okay, there is something in here and here. Then we figured out this order statistic approach. So that gave us a clean result. So here is the first remark. The probability that the type 1 error of this classifier exceeds alpha is under a constant that only depends on K and alpha. We call this probability the violation rate of this classifier, and we denote this upper bound by VK. So we know that when the TIs, the classification scores are continuous, when the big F is continuous, then this bound is tight. The second remark is that because we want to find the smallest threshold that satisfies the type 1 error control, then among all the Ks whose VK are under delta, we pick the minimum and we denote as K star. So that will be the order we pick for the threshold. And our third remark is that to be able to make this algorithm work, we have a minimum sample size requirement. And this is on the number of observations in the left out class 0. Otherwise, we may not have any K whose VK is controlled under delta. So we can simply find this by inputting this K star equal to N, and then we say what will be the N such that Vn is less or equal than delta, and we can find this is the result for that. So to give you an example, if we set delta, the violation rate upper bound to be 0.05, and alpha, the type 1 error upper bound to be 0.05, then this ratio is about 200. So we need roughly that many data points to satisfy this. Okay.
Sorry, can you go back 2 slides again?
Yeah.
So one more slide to remark 1.
Yeah.
So here the probability that the type 1 error depends only on K and alpha.
Yes. No, it's the it's the violation rate only depends on K and alpha. So this is this thing. So this thing only depends on K and alpha, and type 1 error is here. So it's about the probability that the type 1 error exceeds alpha.
So this doesn't depend. So this doesn't depend on the type of
2
fee,
error, you mean?
right? It doesn't depend on the type of fee that you're using, like logistic or whatever.
It doesn't depend. But it's exactly right. So it doesn't depend. But this will only give you an order. So this will only give you the order K star. But the threshold, you need to input this K star back into this classification scores to find the K star order. And that value will depend on the classification algorithm.
So what is there, I guess, what's the role of potentially overfitting? I mean, suppose I use like a linear classifier versus a classifier that can be extremely wiggly. Is that reflected somewhere in your results?
I think it's actually because we are calculating the classification scores in the left out sample, so which is not used for training. So in your case, if it's overfitting, then, okay, I should say this. So you made a very nice point today. So regardless of whether you overfit or not, our approach here will always control the population type 1 error under alpha with high probability. But what we cannot say is the type 2 error. The type 2 error may end up being very bad. Yeah.
Okay.
Yeah, so the thing is that even for a very bad classifier, you still can always control the type 1 error.
And then for your dependence of the sample size, that doesn't, is that affect, sorry, first of all, what sample size is that? That's the sample
size is the left out class 0 sample. So you need to have at least that number of left out class 0 from your training data to guarantee this high probability control on the population type 1 error.
Okay, so that's why that doesn't depend on the complexity of your classifier either, right?
No, neither. Okay. Yeah, so all the issues about the classification accuracy, overfitting, complexity, those will actually put into the type 2 error.
Okay.
Yeah.
Okay.
Yeah.
Thanks.
Thanks. Okay, so here is a summary about what we actually did in the algorithm. So our input will be training data, and that's a mixed IID sample composed of some class 0 and class 1. And we have an alpha as the type 1 error upper bound. And we have delta as a small tolerance level, which should be very small. And M is the number of random splits. So by default, we do one random split, but because of for the algorithm stability and also robustness, we can increase this to be greater than 1. So this function is based on that proposition. So it helps us to find that order K star just based on the left out size N and alpha and delta. So we just do what I just said, right? We found this K star and return K star. And this is the main function we call NP classifier. So we input the mixed training data, alpha, delta, number of splits. So we first randomly split the training data's class 0 points into 2 halves. And we define this half as size as M. And then we input this N, alpha, delta to that rank threshold function to get K star. Then we start the random split. So for a total of capital M splits, each time we randomly split the class 0 into 2 halves, and we pair one half with class 1 to form the mixed sample, and the other half is what we call the left out class 0 data point. And then we put this mixed sample into a classification algorithm to get a scoring function. Here we call it Fi. Okay, and after obtaining the scoring function, we use it with each left out class 0 So we get FIX1 to FIXN. So we give them some notation called TI1 to TIN. Those are the candidate thresholds. And we sort them from the smallest to the largest. And then we find the K stars, which K starts from here, and that will give us the threshold. Then the train scoring function and the threshold give us a classifier. So this is an NP classifier based on our algorithm. And if we do multiple random splits, we will have multiple NP classifiers, and we ensemble them into one classifier by majority vote. That will be the last step. So this is the algorithm, and it will control the population type of error with high probability. So then back to this toy example, we apply that algorithm and see what happens. This is what we get. So if we construct 1,000 classifiers, one per simulation, then we get the distribution of their population type of error, still based on that closed form formula. Then we see, yes, most of them are under alpha, and the proportion that exceeds alpha is controlled under delta. So we have 4.1%, and our delta is 5%. So we control the population type of error. And based on that, we built upon what we call NP-ROC bands. So here in our illustration, we try to address the issue that the ROC only plots the empirical type 1 error. Here we can plot our alpha, the population type 1 error upper bound. And correspondingly, for each classification method, given each alpha, we found an upper bound and lower bound for its type 2 error. And so this type 2 error, I just want to make it a little more specific, is actually, we can say it's actually conditional population type 2 error, which means that we're still looking at the population type 2 error, but we're conditioning on training. So that's what we define here. So we can see that this will give us an idea about how different classification methods, say one is logistic regression, one is random forest, can perform at a specific alpha, so given the type 1 error upper bound. So you can see that the red one is doing better when alpha is small, but the black one is doing better when alpha is big, is large. And this can also give us some guidance if we do not know which alpha should we expect, right? So if we see that, okay, after we increase alpha a little bigger, then the type 2 error drops sharply, or 1 minus type 2 error rises sharply, then that might maybe a good alpha we would want to pick. So it can give us some data-driven idea about what alpha will be okay or will be reasonable given the algorithm you pick. So back to Dave's question. So if the algorithm is doing very poorly, then we will expect that even though we can control the type 1 error under alpha, but this curve will be very low at the alpha.
May I interrupt?
Yeah.
I'd like to interrupt. Could you tell me what the distribution is that for which that picture is developed? Presumably to get upper and lower bounds, you have to know what the true distributions are.
Okay, so actually I can give a brief description about how we made this figure. So the distribution here, we're generating just from Gaussian. So that's the simulation example. But to be able to construct the bars or the bands, what we are doing is still relying on that sample splitting. But in that case, we need to leave out some class 1 for us to obtain the upper bound and lower bound. So we're still relying on order statistic, and we're not really using any probability or parametric assumptions on the data distribution.
Thank you.
Yeah, thank you. Okay, so this is the screenshot of the paper, if in case you're interested in reading further. And this is the R package for implementing the whole thing. So if you have any questions, please feel free to email me or any of the co-authors about your questions. So far we have a lot of downloads of this package, which makes us very happy. So here I want to just, before I wrap up, I just want to quickly tell a little bit about what we have been doing recently. So there are 2 paradigms. I talked about NP, and the one that has been used a lot in practice is called a cost-sensitive paradigm. So as I said previously, right, this is a very natural formulation. in the oracle sense or at the population level, we add weights, C and 1 minus C. So C is a number between 0 and 1 as weights to the R0 and R1, and we minimize this weighted sum. So you see, in the oracle sense, we know there is a 1-to-1 correspondence between C and alpha, right? There's some duality. But if we look at the sample level, it's a lot more complicated. So under cost-sensitive learning paradigm, there are many algorithms that are doing the weighting at different levels. They can do a pre-training, which means that they can just resampling the class 0 and class 1 data points to change their weights. Or they can do in-training as here, right? In their objective function, they change the weight by plugging the empirical type 1, type 2. Or they can do a post-training. After they obtain the posterior probabilities, they change the weight over there. So there are approaches, all sorts of approaches out there. And for NP, in practice, we would use, in general, we will use this NP umbrella algorithm because it's the most flexible one, do not have assumptions on the data distribution. It's just on the independence of data points. So in practice, how do we link those two, right? So there's no direct one-to-one correspondence at the sample level between C and alpha. And why is this important? Why do we care about this? Because the advantages and disadvantages of the two paradigms are complementary. So for cost-sensitive classification, advantages, it's easy to implement. It doesn't need sample splitting. So basically, when your training sample size is not so big, you may want to save them all for training. And it has wide application practice. But the disadvantages is that there's no consensus to assign the costs, especially if you care about the population type 1 error alpha, then there's no direct way to do that in the cost. In contrast, what I just talked about, the Neyman-Pearson classification, it has good theoretical control on the population type 1 error, but its umbrella algorithm requires sample splitting, which will reduce the training sample size. So if we can find a way to link the two and combine their advantages, that would be nice. So in our ongoing work with my former student and my collaborator, Shane, so what we have been doing is that we try to find a high probability upper bound on the population type 1 error of a classifier constrained by cost-sensitive learning. And we realized that we cannot get an exact alpha. So what we take is that we try to estimate this alpha given a pre-trained classifier, given the training data, and given the delta. So we hope we can find a good estimate about alpha. So we hope that our manuscript on this topic will be posted soon. And another thing of our recent work, which is available on arXiv, is that we try to do feature ranking in classification under the NP paradigm we just mentioned. So suppose that we really care about controlling the type 1 error under alpha, then our feature ranking criteria should also reflect that alpha. So that's the motivation behind this work. So finally, this is a summary of what I just talked about. I introduced this problem in binary classification, and the key question was just what Dr. Liang asked about where is the randomness. Hopefully we can have some more discussion on that. And I talked about the NP classification, the framework, and the umbrella algorithm. And I briefly showed one slide about the NP-ROC band and our recent work about bridging cost-sensitive learning and NP and feature ranking under NP. So lastly, I want to thank my collaborators and my former student and current student for their great work and for the funding agencies that have been supporting my research. So last but not least, I just want to quickly show a glimpse of the package. It's available on CRAM. It's easy to install and load, right? And I just show a very simple toy example again from Logistic regression. So this is a two-dimensional feature space, and we have two labels. So if we directly run logistic regression, just using the GLM function, right? And by default, we get a classifier. If we look at what is their type 1 error on a large test data, which we can say is approximate to the population type 1 error, we see that it's around this range. And if we run our MPC function and we set alpha to be 0.05, here I didn't set delta, the default is 0.05, then we can see we end up having the type 1 error much smaller, and that's what we designed. Okay, so that's all. Thank you very much.
I guess this is where we would clap. I'll clap. Maybe you can hear me.
Thank you.
Can I ask a quick question, actually?
Yes, of course.
I'm still a little bit confused about the cause-sensitive learning paradigm versus this paradigm, because
Yes.
as you said, there's a duality here. So let's
Yes,
take
in the
Oracle.
population. Yeah.
Right. So let's take the Oracle situation where you know
Yeah.
everything.
Yeah.
Can't you work out the relationship between the, for example, Lagrange multiplier for the NP problem and the weights for the Oracle problem? And that probably will involve characteristics of phi or something. And then can't you just directly minimize?
Yeah, so actually, so back to your question. Yes, Dave. So if we just directly use in the practical classifier here, right? If we directly do this, so like say, CS does this, use the R0 hat and R1 hat. And if our NP also do the plugin R1 hat, R0 hat, yes, the duality still exists. But then the duality is about the alpha, which would be a upper bound on the empirical type 1 error, not on the population type 1 error. And the key difficulty is because in the implementation, the NP classifier is using that umbrella algorithm with sample splitting and left out sample to construct classifier. While in the CS paradigm, there are all sorts of ways of constructing the classifier. So that's why it's not possible to have a closed form solution as in the Oracle sense.
I'm still, sorry, so I still am a little confused about that, because it seems like if you can express, I guess I'm confused because you're pointing out that there's a difficulty with overfitting, essentially, right? The empirical type 1 error is not the same as the population type 1 error.
It's not the same, it's not the population error, exactly.
Right.
And yeah.
But these empirical risk minimization approaches are meant to address the overfitting problem.
Right, it's actually, I don't think it's overfitting. The thing is that I don't think it's overfitting. The thing is that we can have an unbiased, maybe if we talk about from the estimation perspective, we can have an unbiased estimate of the population type 1 error, right? So if we have an R0 hat, which is unbiased for R0, that's unbiased. And so we don't have overfitting there, but but R hat value cannot tell us whether R0 value is under alpha or not. So that's the difficulty. So we want to control the R0 with under alpha with high probability, but with R0 hat, we cannot do it.
Can I do that? Sorry, yes.
Yes.
That's the same question.
Dave,
yes.
Can I jump in?
Yeah.
I think Jessica, maybe I'll ask a question maybe that will help clear Dave's question. So Jessica, in your NP algorithm, in your umbrella algorithm, if somehow I randomly pick a classifier, I don't even use any training data, but then go through your, evaluating the type, like the error controlling everything, is still a valid, NP. Like it still has a desired, it's so back to Dave's question, I think that it's different because in some sense, I think there are mismatch about doing a lot of a training on half of the data, because the loss function has nothing to do with the goal here, the NP type 1 error, type 2 error, because you could have a totally different loss function. So, and you can just randomly generate coefficients for logistic regression, and then go through that pipeline is still a valid classifier with the desired controlling rates.
Yes, that's right. But your type 2 error will blow up. It may be as high as like 0.9 or 0.9.
Right. And my type 1 error could be wrong. Yeah,
I think
right. But actually, that might give you some idea to combination, though. You can just, because evaluating them so easy, you can combine them.
That's related to my question, actually.
Yeah.
But I guess a more mathematical way to frame my question is, suppose you can show, and I'm sure you can show, that R hat converges to R0 uniformly in phi.
Yeah.
If it's uniform in phi, then you don't have to worry about this, right? You can just train phi, get a phi hat, plug it in, and if it's uniform convergence, then you are guaranteed to get to the population type 1 error,
Exactly.
right?
So actually, yeah, this is something I didn't talk about here, but it's actually, so Dave, you're interested, you can check it out here. So in this paper, we do have some results like that. So here we can show that theoretical convergence. So, but basically what we try to show is that with the type 1 error, population type 1 error controlled under alpha with high probability, the type 2 error, the empirical, the population type 2 error of a classifier constrained by plug-in the density ratio, that is okay for one-dimensional feature. So that density ratio and the Oracle classifier's population type 2 error, these two things will be very close to each other. So we can show that for the density ratio classifiers. But here, if we're not talking about density ratio classifier, but in general, any classification algorithm, the difficult thing here is that we do not really have a good oracle. So what would be the definition of the good oracle, say for random forest? Then that would be, just imagine you have infinite number of training data, probably you can define it that way. But there's not a good oracle there, not the minimizer of the, not this one. But you were talking about the R0 hat and R0 and R1 hat and R1 for the same classifier, right? That's what you're talking about.
Yes.
Yeah.
I'm mostly referring to the fact that an empirical type 1 error not being always the same as a population type 1 error is not an issue if you have uniform convergence.
Right. So actually, maybe to be kind of related to your question, this setup is actually related to, this is a question which I first encountered myself when I started working on this. So maybe I should go back here. So yeah, in the early work in the engineering community, they are exactly right. So they try to control this R0 under alpha plus some small epsilon. So if you allow that, then you can control R0 hat because your upper bound can be relaxed a little bit. But in their new formulation, in the NP classification, they require a stringent upper bound alpha on R0. So that complicates the whole issue.
I see. Okay.
Yeah.
Okay. That makes sense. Okay, thank you.
Yeah, thank you, Dave. But I agree with you. I think that theoretical formulation gave us a lot of trouble, to be honest.
Okay.
Yeah.
So Dave, Jessica, oh,
Yes.
Sorry, Steve, go ahead.
I'm not sure this is a reasonable question, but let me ask it anyway. Since the type 2 error is what's going to control what is a good classifier and a bad one, in theory, one could ask the question, how do you pick a good classifier to do well with the type 2 error?
Yeah.
And you know, the Oracle Neyman-Pearson lemma will tell you it's got to be a likelihood ratio sort of thing.
Yeah.
So in theory, there ought to be some sort of a way of looking at empirical likelihood or something like that to kind of get some feeling for what the better classifiers will look like.
Yes, exactly. Yeah, exactly. That's actually this paper, 2013 paper that was talking about the plug-in approach. So basically, they try to address this issue by saying, okay, if we have just low dimensional features, like say the number of features 1 or 2, we can use kernel density estimator to construct the density ratio and use that as a classifier. And that has that nice theoretical property empowered by the Neyman-Pearson lemma. And later, they formulated this in a high dimensional setting. But unfortunately, this has very strong assumptions because otherwise the density estimation would not even be possible. So that's why I think it's still a very difficult question for classification because often the feature number is very large.
Okay, thank you.
Thank you.
So Jessica, I think my question is sort of related with Steve's question.
Yeah.
So could you go back to that slide you show the NP and the ordinary like cost-effective loss function?
Oh, yeah.
Towards the end of your talk.
Yes, yes.
Yeah.
Okay, here.
Oh no, like the equation.
You mean?
Oh yeah, this one is okay. Yeah, I guess. Could you go to the previous slide?
Yeah, this one.
Oh yeah, this one. Yeah, I think one of the difference between the CS and NP is in CS we could come with a classifier conditioning on X, meaning we just learn the probability of Y equal to 1 given X because that cutoff is determined by C. But in NP, somehow the marginal distribution of X becomes relevant now because you want sort of integrated, like the type 1 error have to integrate over X. This is why I think you mentioned earlier, if my feature vector X becomes high dimensional,
right,
the ordinary logistic regression, which is basically learn Y given X,
yes.
Like it's missing because you still need to learn how the margin of X is distributed. So you would get into trouble.
I see.
Well, I don't know whether I got it right. When you say that low dimension, high dimension, I think that refers to dimension of X.
Yeah, it's
because
the dimension of X. Yeah.
Yeah, the usual cost effective, I think the optimal classifier is based on Y given X. So you can just learn Y given X.
Similar to the base classifier, right?
Yeah, right. But in the NP, I think somehow you need to know something about the margin of X, which could be very difficult.
That's actually, very nice insight, actually. That's actually related to the trouble I said. For NP, we need to determine that threshold. But for the classical, or even the CS, without the threshold will remain as 1/2, like in the logistic regression case.
Right. Because you don't, it's slightly different. Yeah. Okay.
Yeah. Thank you for the
nice talk. Thank you.
Could you look at the example, the graph that you gave for that last example? You said that they were, you were comparing the CS and the NP classifiers. Where was the cutoffs? How do they differ? And there you had a graph of a scatter plot of the.
Oh, this one. This is not. There's no CS. It's just this is a demo of the package, our NP package. Yeah.
Oh, and you haven't superimposed what the actual data and the cutoff is.
We don't have but actually we have a figure about the illustration, but I didn't include it here. So basically I can briefly discuss what will happen, right? So if we are just in the logistic regression, right? So we will have a linear boundary that try to separate the two classes well. Right here, black means class 0, red means class 1. So if I'm under NP and I want to control the type 1 error to be very small, then my threshold will shift it towards the red a little bit more. So I won't control the type 1 error to be small. So the boundaries will be different. So back to Dr. Feng Liang's question. Yes, in the CS, when you change the weight of the two things, yes, we can still have that boundary shift, and that can correspond to the NP. And actually, I didn't say, but in that case, if we do this, sorry, I go back here. If we do this post-training CS, exactly, we can find a 1-to-1 correspondence with NP because we both rely on the same training and we just adjust the threshold. But if it's in training or pre-training, then that's a little bit complicated.
Yeah, thank you. That's sort of what I was going to try to get at. But thank you very much. That was a very nice talk.
Thank you. Thank you so much for attending. Do we have more questions from the audience?
Basic question.
Yes, please go ahead.
So in the Neyman-Pearson setting, usually the classical way is to just set a threshold for the density ratio, for the likelihood ratio. And here you are first computing a certain statistic, capital T, based on the X, maybe using the logistic regression as an doing test for capital T.
Yeah.
But then you just assume that the optimal test should be based on T bigger than some small t.
Yeah, that's also assumed, right? That's already relying on the algorithm, right? Because we rely on the algorithm to get the t's, and the algorithm itself does a thresholding on the t to output a classifier.
My question is, did you just assume that the likelihood ratio for capital T is monotonic in T? In other words, is it possible, a priori, is it possible that the optimal decision region for capital T is some
Right, that's a very good point, exactly. Yes, here, yes, so that's what I said here. So what we are looking at is this, what we call the scoring type of classifier. So basically, this is the type of classifier we're looking at. And so its scores are monotone. So the larger the score, the more likely we predict as 1.
Okay.
Yeah, but you're saying about other possible classification methods whose decision region may not be one direction, right?
Yeah, so yeah, that answers my question. I think I missed this one.
Yeah, thank you for the question. And that clarifies it, yeah. Okay, thank you.
Can I use the maybe to solve the high dimensional problem, maybe I can first use some feature selection algorithm to go to a smaller set of features and then apply density.
Definitely, yeah, definitely. That's also possible, because that's why we say it's an umbrella algorithm, because we leave a lot of the previous choices to the users. Yeah.
Okay, so
yeah. So for example, if you can do some even dimension reduction, right? If you reduce the feature number to a small number of combined dimension, let's say principal components, then you can, if the number is already very small, say 1 or 2, then you can use the kernel density estimation to get a density ratio classifier. That's possible.
Okay, so is there any optimal, some results that still may not have been proved using the existing work? So in other words, is there anything that is left open after all these algorithms have been proposed?
I would say, in my opinion, I think if we want to have total freedom about our algorithm choice, probably the NP umbrella algorithm is the way to go. But still, like I said, my collaborators and his collaborators, they have been working on this new parametric thing. So this one is actually about reducing the sample splitting, but using, I think they are studying the LDA model, sparse LDA model for high dimensional data. So under that model setup, they can find a threshold without using sample splitting, without using the NP umbrella algorithm at all. So, but there's always some prices to pay if we don't want to sacrifice sample size. And also but I don't think this is about optimality either. So if we care about the oracle property, then we have to rely on the plugin. So because that's just the thing based on the Neyman-Pearson lemma. Yeah, so to be honest, like our NP umbrella algorithm, even though we adopted the NP name, but what we only keep is the control of type 1 error under high probability. That's the only thing we keep. We are no longer talking about the optimality of the type 2 error. We're just talking about the optimality of type 2 error under that specific algorithm choice. So given the algorithm, given the training, then what would be the threshold that gives us the smallest type 2 error? That's the only thing we're trying to do.
Okay, thanks for your answer.
Thank you.
Are there any other questions? I guess if there are, we have her recording. We can go back and look at it, and we can email you.
Yeah, I can also share my slides if you'd like to.
Yeah.
Yeah.
Then thanks a lot for being
Thanks a lot
our inaugural speaker.
Yeah, it was a nice discussion. Thank you everyone for attending.
Thank you. And then we'll see you tomorrow for the meetings, right?
Yeah, we'll see you tomorrow. I'll look forward to the schedule from Emma.
Cool.
Yeah. Thank you.
Thanks, everyone.
Thanks.
Bye.
Bye.